In today's video, we're doing partial derivative, and for our two questions today, it's going to be a more basic one where we're trying to find the partial derivative, and in the second problem, we're trying to do the opposite where we're given the partial derivative and trying to compute the original function back. So first of all, let's focus on our first question, a more basic question on partial derivatives. So partial derivatives are used in multivariable calculus because in multivariable calculus, we don't only have x values, but we also have y values or z values, for example. And in order to compute derivatives, we have to partially derive them. So in our first problem, we want to find fx and fy if our function f of xy equals to x cubed plus y squared times e to the power of x. And first of all, the notation fx and fy means the derivative with respect to x and y. So for example, fx, the derivative of that, we will denote that as df by dx. So meaning that we're trying to derive a function with respect to x. So in single variable calculus, we learn, for example, y equals to x squared. If we want to find the derivative, we would use the term y prime, or sometimes we even do dy by dx, right? Because y is our function and x is what we're trying to derive, and in this case, it's going to be 2x. In multivariable, because we have another variable, we don't only have x values, we also have y values. So we do this symbol. So notice that the d here is like written like that because it represents partial derivative. Whereas in single variable calculus, we have just the regular letter d. But that's not too important for today's video. Really, we're trying to find the partial derivative. Likewise, for fy, it would be with respect to y. So what I mean is, if we have fx, we're trying to derive only x, and we're treating y as a constant, whereas in fy, we're treating x as a constant and trying to derive y. So to make things simpler, let's try doing this problem. So we have our function here, and we're trying to find fx and fy. So first, let's focus on fx. So fx, we're trying to derive x and ignore, not necessarily ignore y, but treat y as a constant. So let's say, to make things easier, let's say y is 5, for example. If we were to derive this, we have x cubed plus 5e to the power of x. We want to try to derive this, that would be 3x squared plus just 5e to the power of x, because the derivative of e to the power of x is just e to the power of x. And if we have a constant, we just multiply that. So we are basically doing that when we're trying to solve for fx. Instead, we leave y squared as a constant. So we treat it as like a number like 5. So to put that as our actual answer, the derivative of x cubed, as we mentioned, is 3x squared. And the derivative of y squared times e to the power of x, remember, we're trying to treat y squared as a constant, so it would just be y squared times e to the power of x. So notice how this is kind of like similar. We are basically treating y as a constant, which is why I chose it as a number, just to make it easier to understand. But that is the main idea. And to do fy now, we are doing the opposite, where we treat x as a constant. So if we treat x as a constant, that would just disappear, right? Because let's say x is like just a random constant. Let's just say c, right? Plus y squared e to the power of c. These are just numbers, right? And so if we derive with respect to y, the c in the beginning would cancel out, and this is just a constant, so we just leave it like as e to the power of c, that's a constant, and then we derive y squared, which is just 2y. So that is kind of like the idea. So our answer would then be just 2y, because that is the derivative of y squared, and then we multiply by our constant e to the power of x. And there you have it. That is how you find fx and fy. And some problems, they might ask you to also find like at a specific point a, b. Then in that case, we just plug in a into x and b into y. but we are not asked to do that in this problem, so we're good. So that is our answer. In our second problem, this is more difficult because this time instead of giving fxy in our question, we're given the opposite. Instead, we're given the partial derivative. Note g is just like f, we just call it differently. It's like f of x and g of x, basically same thing. But this problem is harder because we're not given g of xy. Instead, we're trying to find g of xy. On the right here, I wrote like a step-by-step process, pretty simple, but it is hard when you try to do it yourself, so we're gonna do it together. So for our first question here, or not first question, our second question, we're given gx equals to 2x plus y, gy equals to x plus 3y squared, and we're given the point. And the first step we want to do, notice here, number one, we want to have the fx, and we want to integrate it to get f, right? So we're given gx, so gx equals to 2x plus y, and we want to know what g is. And to find what g is, remember the notation, fx and fy means the partial derivative, so this itself is the partial derivative, and we're trying to do the opposite. So the opposite of deriving is integrating, right? So in order to do this problem, we're gonna have to integrate this, and we're gonna get, and remember when we're integrating, it's with respect to x, so again, treat y as a constant. So if we were to integrate this, first we have 2x, the integral of 2x is gonna be x squared. And remember, because we're integrating x because we are doing it with respect to x, but y on the other hand, be careful not to do y squared over 2. That's incorrect because we're integrating based on x. So y is a constant. So if y is a constant, we would just multiply by x. And remember, in integrals, we have to always plus c, but be careful because we are dealing with multivariable calculus, we would just annotate that as g of yz, which is basically just kind of acting like c, a constant. After our first step, our second step is to find fy based on what we found here. So from here, we gotta find gy. So here is where things get messy because we notice that we are given what gy is, but we want to first find it out ourselves so then we can compare. So ignore the question for now and only compute gy based on this equation. So now we're going back to deriving, but because this is our integrals, so we have to compute gy. So remember, kind of connecting back to what we learned earlier, we're trying to find fy, meaning we are treating x as a constant and deriving y, deriving with respect to y. So here we have x squared. So x squared is just a constant, so that disappears, so we don't have x squared. And then we have y times x, and to derive with respect to y, we're treating x as a constant, so if, let's say this is 5, the answer would just be, the derivative would just be 5, right? So our answer here is just x, and then we have our constant g of yz, and because we don't know what that is, we're adding this y here because we are deriving it, we're doing a partial derivative, so we would just leave our answer like this. And then now what we want to do is compare with what we're given. So we're given, this is what we computed, and I'm going to copy down the question, and this is what we're given. So now we're going to compare these two. So to compare, we do x plus gy of yz equals to what we're given, x plus 3y squared. And we're trying to isolate this. So basically move x to the other side. If we move x to the other side, they both cancel. So our answer for gy of yz equals to 3y squared. And now that we've gotten what that is, our third step is to take this, and now we go back to integrating it. So we are given, or we computed that GYYZ equals to 3y squared. Now we want to solve for g of yz. So this is kind of similar to the process here. It's similar to the process from here to here, right? So from here to here, we're also integrating. So now to integrate 3y squared, remember this time it is integrating with respect to y because we have the y here. So if we integrate that, we get y cubed because 3y squared, the integral of that is y cubed. And again, we have to add a c, and this time we call that h of z. And then for our close to final step, we write back the general equation because we're trying to find what g of xy is. So g of xy is here. We have computed that, but we weren't finished with it. So we can copy that down. We have x squared plus yx plus g of yz. And if we take a look at this, we don't know what gy of z was earlier, but we just computed it, and it was y cubed plus h of z. So this is actually y cubed plus h of z. Remember, our final goal in this question is to find out what g is. In the beginning, we already found out what g is, but we weren't finished with the problem because we didn't know what gy of z is. Now we know what gy of z is, but now we don't know what h of z is. And so our final step is to plug in the values that we're given. We're given that g of 0, 0 equals to 5 here. And we just need to plug that in. So 0, 0 meaning x is 0, y is 0. So if we plug that in here, we get 0 plus 0 times 0 is 0, plus 0, plus h of z, and g of xy is equal to 5. So 5 is equal to h of z. And to finish our last and final step, we just need to copy down what we already wrote and just plug in the missing function of h of z, which is 5. So instead of h of z now, this would be 5. So our final answer is g of xy equals to x squared plus yx plus y cubed plus 5. And that is our answer. So the process is a bit difficult, but as you can see, if you follow the steps correctly, you'll be able to find this final function. And there you have it. Thanks for watching this video on partial derivatives. Thanks for watching the video on partial derivatives. Oh my gosh, derivatives. Thank you for watching the video on partial derivatives, and I'll see you guys next time. Thank you.